Okay, so let me remind you what we did last time. So last time we um, showed that, let's say, under the Gaussianity assumption, which was this E2 assumption, the noise being a normal random vector with mean 0 and covariance sigma squared IN, the response is going to also have that distribution. And then we showed that the joint distribution of beta hat and E would be normal, standard normal, with this mean vector and this covariance matrix. And the key was that by considering this joint distribution, we get to compute something which is not available if you just consider individual beta hat and E. And that's the cross covariance. And this cross covariance term is 0, but turned out to be 0. And because we're in the Gaussian model, we know that independence and uncorrelatedness are the same. And so we conclude that beta hat and E are independent. Okay. So anyone remembers what was the significance of this? So why do we care about this relation between beta hat and E? What was the consequence of this?
They are independent.
Sorry?
They are independent.
Yes, they're independent. That's good. But what is the significance of that? Why do we care about the... So beta hat is an estimator. Why do we care about the E being independent of beta hat? It's an interesting result, but what is the statistical significance of it?
So E is independent of beta hat, so then we can conclude that the E squared, the magnitude E squared, is inside of beta as well.
Okay, why is that?
I'm sorry, I was muted. So
E is independent of beta hat, that's independent. And then we can conclude that this is true. So why this is true?
what I understand it is generally if two random vector x and y are independent, then any function of x is independent of any function of y.
Great, great. Yeah, so any function of E would be independent of any function of beta hat. And so this in particular is a function of E. And this, of course, is a function of beta hat. So we conclude this. Okay, that's for independence. So independence is strong in that sense. Okay, now, so what is the significance of this now? What can we conclude here?
They are independent for any measurable function f and g, so E squared.
No, yeah, okay, yeah, that's fine. So we have this. Now, why do we care about this? What is the significance of this? Anyone?
In MBN family uncorrelatedness, something like that.
So in MVN family, uncorrelated is equivalent to independence. So that's where we used it. So we use that. At this point, this is not normal. So you're out of the normal family. But I'm not saying why this is true. We established why this is true. So why do we care about this? What is the point of this? It's an interesting result, but why do we go into so much trouble establishing something like this?
Is it because mu hat is a function of b hat, so the e squared would be independent of mu hat?
Okay, so you're saying mu hat is a function of beta hat, right? That's
yeah.
So we can conclude that this guy is independent of mu hat. This is true because mu hat is a function of beta hat. But now I'm going to ask, what is the significance of this? True. True. Mu hat is a function of beta. This is good. This is a good observation. But you could have said it here as well. So E is independent of mu hat. There is a bit of significance to this because so it's good that you pointed out. So this is also true by the same argument. The reason is that I can write y as mu hat plus e, right? So what do we know about the relation, geometric relation of mu hat and e? Right, we know that, so let me maybe put this somewhere cleaner.
Are they complements in the subspace?
They belong to complementary subspaces, yes. So let's try. Side note. So side note. E is independent of mu hat since mu hat is x beta hat is a function of beta hat. And I know that y can be written as e plus mu hat. And so this belongs to the image of x perp. This belongs to the image of x. So they're in complementary subspaces. So I'm going to not write it this way. What we know is that we know that they're orthogonal. E is orthogonal to mu hat. Orthogonal because of the way we constructed the projection and all that stuff. We have now shown that under E2, E is in fact independent of mu hat as well. So this is statistical. This is geometric. So not only they're orthogonal as vectors, as random vectors, they're independent. So this is much more than orthogonality. So you could have two vectors that are orthogonal, but not necessarily independent. Whereas statistical independence is something about the aggregate behavior. If you do it over many experiments, the probability of E being in a set and mu hat being in a different set, that factorizes, sort of. So, okay, so this has some interesting significance, but that was not what I was going for. What I was going for is that, so is this clear so far? It's an interesting observation, but what I was hoping to you guys to say is that S squared is independent of beta hat. Okay, because this is E squared over n minus p plus 1. So it's a function of E, a function of E squared or E. And so this is true. And the significance is that the two estimates are independent. We have an estimate for the variance, and we have an estimate for the coefficient vector, and these two estimates as random objects are independent. And so this is going to be useful for us later. Okay. Good. So I believe I talked about this last time. The last thing is we need the distribution of s squared. So we know the distribution of beta hat. We know that s squared is independent. Know this. Distribution of this. We know that s squared is independent of beta hat. We don't know the distribution of s squared. Later on, we'll establish this distribution, and it turns out that the norm of E squared divided by sigma squared is chi squared with n minus p plus 1 degrees of freedom. And so this indirectly specifies the distribution of s squared. So if I look at this, this is just s squared is just sigma squared divided by n minus p minus 1 times E squared divided by sigma squared. So it's a scaled multiple of a chi-square distribution. So this has, I'm not going to write it, but it's just a scalar multiple of a chi-square distribution, or has a scaled multiple of a chi-square distribution. And then I also argued that you could do a little bit of calculation, because the expectation of a chi-squared random variable is equal to the degrees of freedom. And so you get that the expectation of this is this constant times the expectation of this, and the expectation of this is n minus p minus 1. So these would cancel out, and you get the expectation of s squared is sigma, which is sigma squared, which is showing that this is unbiased for sigma squared. So this was last time. There is another way of saying that the expectation of E squared is sigma squared, and that's by noting that this turns out to be the trace of the covariance matrix of E. The trace is just the sum of the diagonal entries. And so this would be sigma squared trace of I minus h. And the trace of I minus h would be equal to the rank of I minus h, because I minus h is a projection matrix. And the rank of this is just n minus p plus 1. So I go over this argument, which is sort of optional, but elements of this you have to know at some point. This discussed in previous lecture videos. So look at probably either 2020 or 2021, I think last quarter. I think probably I go over this in detail, most likely in these videos. So have a look at those videos, and if you have questions, we can go over them in a subsequent discussion.
Do we need the sigma square in front of trace I minus?
Yes. So I'm talking about the trace here. So the trace is that in the end, this would be sigma squared times n minus p minus 1. Yeah, so the trace is going to be the rank for a projection matrix, and the rank of I minus h is just the dimension of the space onto which it projects. So the dimension of the space onto which h projects is p plus 1. That's the rank of x, basically. And the rank of I minus h is the dimension of the complementary subspace, image of x perp, which adds up to n. So if you go back, we're using the fact that the dimension of v plus dimension of v perp is n, the dimension of this whole space. So this would be, in our case, p plus 1, because v is the image of x. And so dimension of v perp would be n minus p plus 1. But I talk about this later in this one. Right. Okay. So can you walk us through what is the purpose of these slides, or what are we trying to do here?
So the purpose is just the building confidence interval, and the pivot construction. It's just like observations and the parameter are important part.
You broke up a little bit. So what is the, so,
And
okay, so let's say we want to construct confidence interval.
Yeah.
So one of the advantages of, go ahead. Yeah, go ahead. So you were breaking up. So what is what is the procedure for building a confidence interval? So let me set it up. So what we want to do, so sometimes statistical inferences refer to the procedure that provides some uncertainty quantification. So sometimes statistical inference is referred to as just inferring the parameter. So we have already done some statistical inference. So we had a model, we inferred the parameters. But sometimes when they statisticians talk about inference, they want a little bit more. So they want not necessarily just the point estimate. So we know like that beta hat, the estimate of beta hat 1 is like 0.05. But this is often not satisfactory for a statistical application, because you want to know whether 0.05 is large or is small, or how uncertain you are. So it's like if I have a random variable whose mean is 0.05, but the variance is like 10, then I could easily be like anywhere between like negative root 10 or root 10. And so 0.5, that difference of 0.5, let's say from 0, is not that significant relative to the variance. So if you have a random variable whose, suppose I have x, let's call it like z, it's normal, which means like 0.5, and the variance is 0.001, okay, then I'm very highly concentrated near this. So if I say that, for example, the value of z is often away from 0, that's going to be true. But however, if I have like a z that's normal between 0.5 and the variance is like 100, this 0.5 is not really that different from 0 for this random variable, because compared to, so this is going to be like 0.5 plus minus, usually you'd get 2 times sigma. So this is like sigma squared. 2 times sigma would be like 10. So with high probability, this is going to be in like about negative 19.5 and 20.5, right? So there is a high chance that we're in this interval, and so we're very uncertain about the location of this. And so if someone asks you whether the value of z, like z is generally non-zero or not, we should probably like stay quiet. We don't know. Whereas here you would get like, let's say 0.01 if you want, add one more, 0.0001, you'd get like this random variable is in like 0.05 plus minus like 2 times about 0.01. So this holds with probability bigger than 95%, with probability bigger than 0.95. 0.95 here, z would belong to this. And this is much better. So it's like 0.0. Negative 0.0, sorry, 48 and 0.52. So I'm with very high probability inside this interval, so I can say, yeah, probably we're getting away from 0. So if you care about whether this random variable is 0 often or not, then we could say with confidence that, yeah, in this case, we're not 0. In this case, we probably don't know. We should. And so this is like often happens in hypothesis testing. So this could be your parameter beta hat, let's say 1. And we know the distribution. Okay, we know the distribution of, as I had we known the distribution, which we have computed, then you can find this distribution and build a confidence interval like this. Okay, and then based on that, so this could be, for example, could be like beta hat 5. Okay. Under the E2 assumption, they're going to be Gaussian. There's going to be some mean. The mean would be beta 5, the true beta. Yeah, so this is not a good example, but you get the idea. Right, so this makes sense to people. So the size of a random variable itself is not necessarily informative unless you know something about the variance. That's the purpose of whatever we're going to do next. The confidence intervals, doing hypothesis testing, doing more sophisticated statistical inference. Does it make sense?
Yes.
Yes. Okay. So suppose now I want to do something like that. I want to. So what is a confidence interval? Sort of. I mean, Sehun, do you remember? Did you get to the part? So we want to build, let's say, a confidence interval for a parameter. So what is a confidence interval? Anyone? Remembers what that is?
A population parameter will fall between a set of values for a certain proportion of time.
Right. So okay. So it's a population for a population parameter. So suppose I have a parameter of interest. Let's say beta I. Beta I is the ith coefficient in the regression. So remember, you have y is equal to x beta plus epsilon, and this beta is like beta 1, beta 2, up to beta p, beta 0. And so these are the true parameters. They're the unobserved parameters for which we have the estimate beta hat 0, beta hat 1, beta hat p. So what we want to find an interval, let's say for beta hat I or beta hat 0, such that with high probability beta 0 is contained in that interval. So the formal proof is something like that. Let's say a 95% confidence interval alpha would be 0.05. For a scalar parameter beta I is a random interval I hat, like A hat, B hat, such that the probability that beta I is in I hat is 1 minus alpha. So the way you interpret this is that this is a frequentist concept. So you interpret the probability as a frequentist using a frequentist interpretation. So what this is saying is that if you run the experiment n times, say, each time we compute this interval, which is going to be a different interval each time because of the randomness. So I get I hat sub or sup I. Then if I compute the fraction of times for which beta I is in I hat I. So that's the notation. So this indicator means this is 1 if beta I belongs to I hat I and 0 otherwise. Okay, so this is basically counting how many of, this is a bad notation again. I think I have done this before. So let's call this J. So this is some fixed J. and then we are counting over I. And so so if beta j belongs to all of them, then this would be n, and this would be 1. But some of them would miss. So you'd have like beta j here, and then your confidence interval in one experiment might be this, in another experiment might be this, in another one might be this, and in one case it would be like something like that, and so on, right? So could be like that, and so you'd go and count how many of these intervals contain the true parameter. So these would contain, this one doesn't, this one contains. So in this case, it would be like 1, 2, 3, 4 would be 4 over 1, 2, 3, 4, 5, 6, right? So roughly 2 over 3, but 0.666. But you have to do it a lot. But this probability, this the way that we calculate, this is called the coverage probability. So this is the coverage probability. And so you want the coverage probability to be 1 minus alpha, or in general, at least 1 minus alpha. You want this to be bigger than or equal to. So you want the probability to be bigger than or equal to 1 minus alpha. And that's the meaning, okay? It doesn't mean that beta j is in any given one. So in any given experiment, there is no guarantee that beta j is in the interval or not. So it's a concept that just shows itself over many runs. It's like an aggregate, like many things in probability. It works out in the long run, or in an experiment with many many draws. So that's the meaning of a confidence interval, right? I should have probably moved the slide earlier. Does this make sense to people?
I had a question. What's like the point of finding like a confidence interval for B hat or just B?
So we correct that. So you don't find a confidence interval for beta hat. You can't find a confidence interval for a parameter. So beta hat is an estimate. It doesn't need a confidence interval. So it's just not defined. So your question would be, what is the point of finding confidence interval for, let's say, beta j, right? That's your question. Is
Yeah.
that... Okay, so anyone can answer that question. What is the point of finding confidence interval for one of these parameters? Anyone knows? Or has some justification for what we're about to do? Diana, do you want to make a guess? So what do you think? Why do we care about confidence interval? So you have probably seen these in the previous courses. Have you seen confidence interval in other courses?
Yeah. The answer that was given in the chat seems pretty good.
Okay, can you measure how precise our parameter estimation is? Yeah, so that's the basic idea. So you want to measure the precision, or the alternative is like the uncertainty of your estimate. And often the reason is that you care about, let's say, a single, generally the confidence interval is that. So the length of the interval tells you, so for example, as I mentioned, if it turns out that you have a confidence interval that looks like this, right? There is a center to it, which is 0.5, and then the length is 0.04. So the length of the interval divided by the center is very small. So this means that your estimate is quite good. So you manage to localize the parameter. Whereas in this case, the length of the interval is like 40. the center is about 0.5, this is very large. And so this shows that your estimate is very uncertain, or like the precision, as you put it. Precision is the like the inverse of uncertainty. So uncertainty usually is measured by the variance. It's not the only way. It's just one of the common ways to measure is the standard deviation and variance, or one over the variance would be called the precision. That's actually a statistical term. So here the precision is very high. So you can see 1 over this is very large, whereas here the precision is small. The other thing is you can use these confidence intervals to do hypothesis testing, as we'll see. And oftentimes you care about a certain value, and if you build a confidence interval, and then let's say I want to test whether beta j is equal to 0 or not. I have a guess that beta j is non-zero, so that would be my null, my alternative. So the null is that beta j is 0 in the model. So beta j being 0 means that the j covariate does not affect the response. So remember, y is like beta j x j plus epsilon. So if we had the j coefficient is 0, it means that the j covariate does not influence the response. So in regression, we care about hypotheses in which the null is like that, and then the alternative, the natural one, would be the beta j is non-zero. So you could build a test for this problem by test statistic by computing confidence interval and see whether the 0 is in that confidence interval or not. And if you reject the null when the interval does not contain the 0, then that would be an interesting test. It would be a test that has type 1 error at most alpha. So another reason we care about the confidence intervals is that you can build naturally build tests out of them that have certain type 1 error probability. I'm going to discuss this later. But the main point was, as was pointed out, is that they allow you to have some measure of the uncertainty. I just want you to understand that what exactly that means. That means exactly this. So as you run the experiment, the probability that these or the fraction of the intervals that would contain the true parameter would be guaranteed to be a certain value, and the length of the interval would like correspond to how uncertain you are. But you care about this because in, let's say, in scientific experiments, so let's say you do 1,000 experiments, and they're not the same. They're not from the same regression problem, but think of them as assume as if they're coming from the same problem. Let's say every drug that people test, whether it has an effect or not, there are thousands, but maybe like hundreds of thousands of these in the medical literature. And if they had a good confidence interval, like 95%, then 95% of those results would be valid, hopefully, if they've done it correctly. And the models are correct. Usually the models are not. The idea that you develop this under certain assumptions, those assumptions are often not true. But assume that the assumptions are true, then they've done the analysis correctly. Then if you like pick a paper from PubMed and look at the result, that particular one might be wrong. But if you look at 1,000 of them, hopefully like 950 of them are valid. At most 50 are wrong. So there's a way of controlling how much or how much wrong or how let's say, yeah, how much it's hard to say, how much problematic results you want to allow to like be there out there in the scientific literature. That's the basic use of these traditional. Does that answer your question? Is this good? Everyone happy with why we do it? See, yeah, okay, yeah. So if you look at like papers in medical journals or even social sciences, any like empirical field, you'd see these results, and then you'd see these confidence intervals. There's like a value, effect size, and then there's a confidence interval. So they do it mostly for controlling the errors or controlling the fraction of wrong, possibly wrong results that are there due to chance. Okay, so how do we build a confidence interval for beta j? Any? Sam, do you remember what the idea was? So let me. So suppose I want to do it for beta j. What is the first step? Build for beta j. So I'm going to help you. There is so the model is this, and you're going to assume E2. So noise is normal 0, sigma squared I, and X, I believe. So it's like X is full rank, has full column rank. Under these, we have calculated, so what is the distribution of beta hat under these assumptions?
Normal distribution.
Sorry?
Normal distribution.
Right, with?
A real beta I. I mean beta j.
Real beta vector, yeah? And the covariance?
Sigma square
Yes.
bj, yeah.
No. What is the covariance matrix?
It's just sigma squared I.
That's a good guess. Is it true? If it were true, it would be very nice.
X transpose X inverse.
Okay, yes. It's not that simple, unfortunately, in general. So we have calculated that's the covariance matrix if you go back. So now let's say I want to do it with beta hat j. I'm going to do it with beta hat I, let's say. I think I've used I before in the slides. So this is going to be, what is the distribution of a single beta hat I? Oh, I already mentioned that it's normal. Why is it normal?
Marginal of ambient. Or
Great, so it's marginal of a multivariate normal distribution. And what are the mean and variance?
beta I and covariance beta I.
Variance of, no, beta I is like constant. So this has a variance. So whatever goes here is going to be the variance of beta hat I.
The sigma square
Yes.
X transpose X inverse I.
Yeah, so it would be the ith entry, right? It would be the ith entry of this. So if you go back and understand what the covariance is, the ith entry of this is going to be the one that's on the ith location on the diagonal. That would be the variance of beta hat I, and sigma squared can come out. And so we have this. I'm going to call this VI. Okay, so you form this matrix, and you look at that entry on the diagonal, and that's a number, so that would be what this is. So this is the real variance of beta hat I. So how do we build a confidence interval now? Suppose I know sigma squared. So if we know sigma squared, can you give me an interval such that? So what is maybe let's see if you can say something about this. Can you give the confidence interval for that?
Can you just put sigma square? Just sigma square, or I'm not sure.
Yeah, you have to come up with an interval that contains beta I. So I want the interval I hat such that I had such that the probability that beta I is an I hat is 1 minus alpha. So what is the distribution of this guy?
Is it normal also?
Yes. Why?
Because so expectation of the beta I hats. I mean, yeah. It
the
follows
fact that is
0 and 1, right?
sorry.
It follows mean 0 and variance 1, right?
Right. Depends. What do you guys think?
Is it because it's a linear combination of two multivariate normal distributions?
Yes, it's in fact like a fine transformation. Transformation of beta hat I. It's just 1 times this plus some constant. You can think of this as normal, but it's better not to think of it like that. Fine transformations of normal random variables are normal. The mean is correct, so the expectation of beta hat I is beta I, so the mean is going to be 0. The variance is not. So what is the variance? Maybe I'm going to call the people. Let's randomly sample. Okay, Penny mentioned something. Variance is the same as beta. Okay, the variance is the same. Why? Why is that? Mary says that constant, okay, good. Constant shifts do not change the variance. That's right. So constant shifts do not change the variance. Okay, then what is the distribution of beta hat minus beta I divided by sigma root vi?
That's why I wanted this normal distribution 0 and variance 1.
Okay, yeah, you were quick to answer. Yeah. So why?
The variance of beta I hat minus beta I over sigma square root vi is we can factor out the sigma square root beta I as a denominator.
So this comes out squared, and then I have the variance of beta hat minus beta I, and this is sigma squared vi. So this would be 1. The mean is 0. Why? This is normal.
Is also fine transformation.
Yes. There's just one word that you have to remember here. Fine transformation of beta hat I. We could have just from the start said that this whole thing is an affine transformation. It's like A times beta hat I plus B. A would be 1 times this. B would be this divided by that. So instead of doing it in 2 steps, we could have done it in 1 step. Now, so if I call this Z, we have shown that this has a standard normal distribution. So the probability that Z, let's say, is in negative 1.97 and 1.97 is 0.95. So this you can use quantiles. So I hope people understand how they construct this. So you go look at the standard normal distribution, and this location is where, if I want 95%, I want this part of the mass to be, sorry, this part I want to have 0.05 over 2 of the mass. I want something symmetric, and this part also 0.05 over 2, and this part would have 0.975. Sorry, this middle would be 0.095. And so if I determine this location, this middle part would be 0.90. The mass would be 0.95 because half of these two together would be 0.05. And so what I need to do is find a location here, this part, which is, so if this side has this much mass, then this side would have, this one would have 0.975 of the mass. So you'd find 0.975 fifth quantile of, or 97.5% quantile or percentile. Normal 0, 1 is roughly 1.97. Maybe I'm wrong, but that's what I remember. It might be like, usually it's like around 2, 1. Let's say that's true. Then, so this you do in R or in you're using a table, you should know something like that. So if I want the 95%, in general, if I want, let's say 1 minus alpha, then I would do 1 minus alpha over 2 quantile here. So I know this. So from this, I get that the probability that beta hat I minus beta I divided by, I'm going to call this gamma, let's say. So this would be negative gamma. So this sigma over root vi, the probability that this is a negative gamma and gamma is 1 minus alpha. And then you can show that this, do for yourself, is equivalent to saying that beta I is in beta hat I minus gamma sigma root vi, and beta hat I plus gamma sigma root vi. Okay. And another way of saying this sigma root vi, this is just the standard deviation of beta hat I. You can see it from here. The square root of this is the standard deviation. So what we have, this is the same thing. What we have shown is that a confidence interval for beta I would be, usually I write it like this, beta hat I plus minus gamma standard deviation of beta hat I. And gamma is the 1 minus over 2 quantile, normal 0, 1. Okay, sounds good? So the point is, so this is called the pivot. It's a quantity that depends on the unknown parameter, beta I, and our estimator. But the distribution does not depend on the unknown parameter. So it's a mix. The pivot could depend on the unknown parameter itself, but the distribution does not depend on the unknown parameter. So that's a pivot. Any combination of statistics and parameters whose distribution is independent of unknown parameter, and you can use this to build a confidence interval, as you can see here. Okay, is this clear?
Yes.
Yes. Okay. So if this is clear, then I'm going to ask you a question. So if you have seen your previous courses, probably you've seen that there is a t-distribution involved in this problem. When you try to compute confidence interval for regression coefficients, then there is a t-distribution with certain degrees of freedom. But we didn't have that here. So what's the deal here? Why can I not just do this? Looks perfectly fine. Anyone? When population PME says when population variance sigma is unknown. Okay, good. So here we assume that we know sigma squared, and you can see that the interval depends on sigma squared. So that in order for me to construct this interval, I need to know sigma squared. And I don't have sigma squared, right? When sigma is unknown, I would run into a problem. Okay, so I'm gonna do this. I'm gonna say I don't know sigma. So unknown if sigma squared is unknown. Um, but we have an estimate of sigma squared, which is s squared, right? So why not replace sigma with its estimate, which would be s, and be done with it, right? So my confidence interval would be beta I plus minus gamma, and then s root vi. What is wrong with this? So I don't have s, I just replace s with sigma with s, which it's an estimate, then seems like we're done.
Standard error.
Sorry?
Standard error.
I don't understand. Under error? Can you like complete your sentence? What is the issue with this? Standard error. So what is standard? What do you mean standard error? This is either a valid confidence interval or not. So can we conclude that gamma still is 1 minus alpha over 2 quanta and 0, 1. Can we conclude that the probability that beta I is in beta I plus minus gamma s root vi is 1 minus alpha? Gamma is 1 minus alpha over 2 quanta of t minus n minus 1. Okay, but why do I need to do that? What is wrong with the present one? Why do I need to change gamma here? Anyone? What would be wrong in this argument? So if you trace back what we did, so we divided by this quantity. So what happens is that if I divide by our estimate, so the argument, if you trace it back, it would be like as if we divided by s. Okay, if I divide by s, then I can't say that this distribution of this is normal, because this is not an affine transformation of beta hat I anymore, because it's an affine transformation, but the coefficients are random, right? Yeah, so S has a chi-square distribution, and S is also functionally dependent with beta hat I, because they're both derives from the same random vector. So S and beta hat I are both functions of your data Y, and so in general they're related. And so not correct because beta at I minus beta I divided by S root VI is not an affine transformation of beta hat I with constant coefficients. S is random, and in general, functionally, dependent on Y, on which beta hat I also depends. Both of them are derived from the same random vector, right? So we know that the distribution of S is related to chi-squared, and we know the distribution of beta. So this will not have a normal 0, 1 distribution. And so because this doesn't have a normal distribution, these probabilities won't be correct. The probability that Z would lie in this is not going to be 0.95 because it's because this distribution is different. So the tails of the distribution behave differently. So the probability that Z belongs to this might be like 0.85 or something like that. And so we need to somehow find the right distribution here and then use the quantiles of that distribution instead. And so the idea is how to find the distribution of this. It turns out that this is also a pivot in general, but the distribution turns out to be a t distribution, not a normal distribution. So as was pointed out, so S doesn't have a chi-square distribution, but it's related. So the key here is even if I know the distribution of S individually and know the distribution of beta hat I individually, that's not going to be enough. It's not enough to know just the distribution of S and beta hat I. So to determine the distribution of this quantity, it is not enough to know the distribution of beta hat I and S individually. What do I need? What do I need that in addition to that? We need the distribution of V1. I'm gonna go ask other guys so that you guys have had like the participation trophy as well. Ethan, do you know what we need? Jake, June, Kaylee. Okay, Kenny again. Not sure. Okay. So Pini says normal divided by chi-squared is t. That's sort of correct, but not completely. There is this missing part. So there is something that we are missing. So if I divide a normal distribution by chi-squared distribution, in general, you can't determine the distribution. First, it's not chi-squared. It's like the square root of chi-squared divided by its degrees of freedom. But let's say that's true. There is something missing. If you give me two random variables that I divide by each other, I know the marginal distributions of each one. I cannot determine the distribution of this unless you give me more information. Denominator and denominator have to be independent. Okay, yes, so in that case, so in this case, denominator and this are independent, and that's the missing information. But in general, what would I need? Even if they were not independent, I could still compute this distribution if I have some information. What is the information in general that I need? Anyone? So what we need is the joint distribution of beta hat and S. So if we calculate the joint distribution, it's like the way that we calculate the joint distribution of beta hat and E. If you have that, then in general we can compute distribution of this, even if they're not independent. So distribution of this is going to be complicated in general, but we have shown that under the E2 assumption, beta hat and S are independent. So one way to specify a joint distribution is if you can say that this has a certain distribution in marginally and this has another distribution and they're independent. Once you say they're independent, then you specify the full joint distribution. Okay, so because of independence, we have the full independence of beta hat and S. That's beta hat is independent of S. We have the full joint distribution of beta hat S, so we're in business. Because we're out of time, I'm going to quickly say it. So what you do is beta hat I minus beta I divided by this. I want to control this. So I'll write this as beta hat I minus beta I divided by sigma root Vi times S divided by, sigma divided by S. Okay, and then I would write this as beta hat I minus beta I divided by sigma root Vi and then divided by S divided by sigma. That's the same. And this would be S squared divided by sigma squared, right? And I'm going to call this step was Z. And this is just Z divided by, this is E squared, divided by sigma squared, and then divided by N minus P minus 1. Okay. So this has a chi-squared with N minus, I'm going to call this D for simplicity. So that I don't have to carry. D is equal to P plus 1. So this has N minus D degrees of freedom. And then these two are independent. So I have a standard normal divided by a chi-square distribution, divided by the square root of a chi-square distribution, divided by its degrees of freedom, and the two are independent. So this then has a t distribution by definition with n minus d degrees of freedom. Okay, so the key is this independence that we established because we already established that you can see this z depends on beta hat and this depends on e, so they are independent. So that's where independence comes in. And so this would have a t n minus d degrees of freedom. So if we use quanta, so gamma equal quanta, the 1 minus alpha over 2th quantile of t n minus d, then we're going to be fine. So you can go back to the argument. It's just instead of a normal, standard normal, we have a t distribution. So this argument here would be just the quantiles of the t distribution instead of the standard norm. And so the only thing that we need to correct is this gamma here. If you don't know the variance. Okay, sounds good. Questions, comments? Okay, for the next time, I would suggest you guys go over the next. So I'm going to post these. So we did this, and then also this, and a bit of this. So there's an example here, and then the discussion hypothesis testing. So I would encourage you to go through as much of this as possible. Okay, and basically can go over everything up to like at least testing a general hypothesis and maybe more.